What gravitons are and could one detect them in TCD universe? What gravitons are in the TCD universe? This question has teased me for decades. It is easy to understand gravitation at a classical level in the TCD framework, but the identification of gravitons has been far from obvious. The second question is whether the new physics provided by TCD could make the detection of gravitons possible. The generalized Kähler structure for Minkowski space as a space of Minkowski space with points replaced by CP2, 8-dimensional space is in question. This leads, together with holography, identified as generalized holomorphy, to the question whether the vielbein part of the spinor connection of Minkowski space, whether it could have interpretation as a gauge potential for gravitation, which spin would take the role of gauge charge. However, the induced M4 spinor connection has a vanishing vielbein curvature. One must forget this option. The M4 Kähler potential, U1 gauge potential, remains the next candidate. The Kähler gauge potential could contribute spin one spin unit to the graviton spin, and this might give hopes for getting graviton in this way. M4 Kähler gauge potential, however, could also contribute to electroweak gauge potential or define a new gauge force. These graviton-like states, if they are possible at all, they would correspond to monopole flux tube, closed monopole flux tubes, and they would contain fermion pairs with rotational angular momentum equal to 1. This would give spin 2. There are, however, grave objections against this idea. It is difficult to understand the value of gravitational constant. It should correspond to CP2 size scale, and it seems that the couplings to matter and antimatter are of opposite sign for gauge potentials. It might be that the spin rotational angular momentum of monopole flux tube could change the situation. I do not know about this. Then there is a further candidate, the trace over a second fundamental form. I denote it by HK. It is identified as a generalized acceleration when one replaces point-like particles with three-dimensional surfaces. It has CP2 part, which behaves like Higgs field. The M4 part, generalization, ordinary acceleration, is like spin 1 particle, and second candidate for gravitation if the additional spin comes from the rotation of the monopole flux tube. This second fundamental form is concentrated at the singularities of spacetime as minimal surfaces and vanishes elsewhere. These singularities are two-dimensional, so that this acceleration would be located to this two-dimensional surface. This would be like Brownian motion, generalization of it. The bosonic field equations imply that the vertex generalizes. Newton's FMR has a generalization corresponding to generalization of point-like particle three-dimensional surface. And this gives rise to the TCD counterpart of Einstein's equations at quantum level, and also at the classical level when one talks about these fundamental space-time surfaces. The interpretation of gravitation as generalized acceleration would conform nicely with the gauge gravitation duality and equivalence principle, so that this seems to be the promising candidate. In TCD one can assign the fundamental vertices with a splitting or closed string-like monopole flux tubes, representing elementary particles. Vertices would correspond to two-dimensional singularities x2, where minimal surface property fails, and generalized holomorphy fails too. There is analog with polo-analytic function. The identification of bosons as bound states of fermions and bound antifermions seems to predict separate conservation of fermion and antifermion numbers. The problem disappears if the boson field in the vertex is replaced with a geometrized classical boson field. Fermion-antifermion pair creation would correspond to the turning of a fermion line backwards in time. There is also a second problem. The TCD counterpart of Dirac action, which would give the vertices, it vanishes identically by field equations outside x2, and there would be no vertices. Could the singularity of this x2 help? Could so-called exotic smooth structures, unique for dimension d equal to 4, and obtained from a standard smooth structure by adding defects, solve the problem? Could the vertex as singularity of minimal surface and of generalized complex structure also correspond to a defect of exotic smooth structure? The four-dimensional spacetime would be completely unique. It would make possible fermion pair creation. There is also question whether gravitons can be detected in a TCD universe. It turns out that protons at the monopole flux tube condensates give rise to a mild optimism in this respect. In the following, a brief summary of some basic ideas of TCD. Next, review of the recent view of classical TCD. In TCD, classical gravitation corresponds to the induced geometry of the space-time surface. It is surface in some 8-dimensional space, Minkowski space, with points replaced by CP2. CP2 comes from the condition that standard model symmetries and gauge potentials are obtained. The gravitational constant, Newton's constant, it should be determined by the square of CP2 radius. This radius is roughly 10,000 times Planck length. If one accepts the hierarchy of Planck constants coming as multiples of its minimal value, which is predicted by the number theoretical vision of TCD, then the effective radius of CP2, about 10 to 4 Planck lengths, would be apart from a numerical scale factor nearly equal to the radius of CP2. One has a formula for G. The embeddability to this 8-dimensional space, embedding space, plus holography, which is forced by the general coordinate invariance, implies that spacetime surfaces are analogs of Bohr orbits. Bohr orbitology would become an exact part of quantum TCD. This gives extremely strong constraints on the spacetime surfaces. They certainly can't directly correspond to the Einsteinian spacetime as a small deformation of Minkowski space. How to realize this holography? Generalized holomorphy provides a realization and gives an exact solution of field equations, general solution. In terms of two functions. To see how this comes, one can first notice that the twist or lift of TCD forces a generalized Kähler structure for M4 and also fixes this embedding space uniquely. This Hamilton-Jacobi structure, as I call it, combines ordinary complex structure and hypercomplex structure together. Also, this embedding space has generalized complex structure with one hypercomplex coordinate and one complex coordinate for Minkowski space and two complex coordinates for CP2. These solutions of field equations correspond to roots of two functions, analytic functions in generalized sense, analytic functions of these four complex coordinates. Hypercomplex and free complex coordinates. And this generalized complex structure in Minkowski space and X4 spacetime surface 2, it corresponds to a slicing by complex partonic 2 surfaces and hypercomplex string vertices, which are transversal or possibly even orthogonal locally. The QFT limit of TCD, what does it mean? First of all, this spacetime surface is extremely complex, many-seated complex surface, topologically non-trivial in all scales. And a single metrically deformed region of M4 should correspond to this surface at least in long-level scales, this Einsteinian spacetime, which is really simple topologically. What this means that gauge potentials of standard model, they correspond to sums of the induced gauge potentials for the spacetime seeds. And same for metrics, for the metric of general relativity. This metric corresponds to the sum of deviations of the induced metric from the Minkowski metric for various spacetime seeds. Holography as holomorphy predicts that spacetime surfaces are analogs of complex submanifolds. The field equations trivialize to algebraic equations, but there is a failure of the minimal surface property at singularities, which are analogs of poles of analytic function, and they would correspond to vertices. This is a big idea. One must start from partonic orbits, which are also singularities. They are three-dimensional topologically, but metrically two-dimensional because they are light-like. The four-metric at them is effectively two-dimensional. This follows from the holomorphy. And this all is due to the change of the metric signature if holography is true. Euclidean region, Minkowskian region, the signature changes. Chern-Simons action is a possible action for partonic surface, but also the four-dimensional action can contribute to vertices at the two-dimensional surfaces at which the minimal surface property fails. And there is analogy with the poles of analytic function and with two-dimensional electrostatics. The contribution of the volume part of field equations, this has delta function like singularity at the singular two surfaces. This volume part corresponds to cosmological constant, which is implied by the twist lift of TCD, which in turn fixes TCD uniquely, the choice of this embedding space. Also, the other parts of action give a delta function like singularity, since field equations must be satisfied also at singularities. The trace of the second fundamental form at the singularity and the similar contributions from the other parts of the action sum up to zero. This trace can be seen as a generalized acceleration for a particle which is now a three-dimensional surface instead of point-like particle. One has analog of Newton's equations and of Einstein's equations at this fundamental level. If modified gamma matrices appearing in the Dirac action are defined by entire action, this would imply supersymmetry. Bosonic action would determine uniquely the Dirac action. Then Dirac action would vanish by Dirac equation. There would be no vertices because ordinary perturbation theory does not work. On the other hand, if these modified gamma matrices, if they are induced gammas defined by the volume action, their divergence is proportional to this trace of second fundamental form and is non-vanishing at the singularities, but vanishes elsewhere. This would mean that this acceleration of this three-dimensional particle would be localized at this two-dimensional surface. It would be like Brownian motion. This trace has CP2 part, call it SK, which is grouped vertically like a Higgs field. And HK can be regarded as a generalization of Higgs. M4 part behaves like a spin-1 field, and Gates gravitation duality of quantum field theory suggests that this gives rise to gravitation as spin 2 rotational states of these monopole flux tubes containing fermion pairs assigned to this second fundamental form. Gravitons as monopole flux tubes carrying one fermion-antifermion pair. This would be the picture. And the additional spin would come from this rotation. Consider next the question what gravitons could be in the TGD universe. Could graviton correspond to a fermion-antifermion pair? This is a question. In TGD, elementary particles correspond to closed monopole flux tubes. They are associated with pairs of two parallel space-time sheets. The Euclidean wormhole contacts at the ends of the closed monopole flux tube. They correspond to three-dimensional light-like orbits of partonic 2 surfaces. They carry point-like fermions, serving as building bricks of all elementary particles. This is a picture. For particles with spin smaller than 2, fermion-antifermion pairs assigned to the partonic orbits carry the spin and electroweak quantum numbers of a particle. But what about graviton? Now fermion pair can give rise to spin 2. The earlier proposal was that graviton spin reduces to fermionic spin. Wormhole contacts would carry a fermion-antifermion pair with spin 1, both of them. And the problem is that it is difficult to understand how the value of the gravitational constant could be coded to the structure of this state. It is neither obvious how the equivalence principle could be realized at the quantum level. The presence of two fermion pairs is, however, not necessary if the monopole flux tube rotates and gives additional contribution to the graviton spin. One could have fermion-antifermion at the wormhole fronts associated with the ends of the string-like object. Rotational angular momentum would allow bosons with spin 2, perhaps also graviton. This picture would conform with holography and the idea that gauge theory at boundaries corresponds to gravitation in the interior. Now boundaries would be these wormhole throats and interior would be this monopole flux tube and wormhole contacts. There are two candidates for graviton. The Minkowski path of the trace of the second fundamental form and M4 Kähler gauge potential. The graviton candidate in question should couple to fermion number. The Kähler option has problems. Gauge bosons couple with opposite signs to fermions and antifermions. Could the rotation of the monopole flux tube cause this problem? Graviton also couples to forward momentum. Could this rotation give rise to this? And then one should understand also the value of gravitational constant. Could this rotation of monopole flux tube solve this problem? There are many problems, and I do not know whether this really works. The trace of the second fundamental form has generalized acceleration and as a generalization of Higgs field. Could it define graviton and Higgs vertices? This is a question. Hk and Mk and also Sk have delta function singularity when the minimal surface property and generalized holomorphy fail. The covariant divergence of the quantity obtained from contravariant induced metric contracted with coordinate gradients or embedding space coordinates gives a trace of the second fundamental form, and it appears in the vertex. It would appear in the vertex. This corresponds to this covariant divergence corresponds to the vector formed by induced gamma matrices. Defines such vector. And this second fundamental form, trace of it is orthogonal to the spacetime surface. In linear Minkowski coordinates, the direct Minkowski contribution to this Mk candidate for graviton vanishes. The presence of the CP2 contribution, however, implies that Mk is non-vanishing and proportional to the radius squared of CP2. This is the key point. As already found, gravitational constant is naturally proportional to this CP2 radius squared. And this trace is vanishing everywhere except at x2 by the holomorphy. And this Mk has been 1 and can contribute to graviton vertex if it corresponds to a rotation, if it is associated with a rotating monopole flux with, say, angular momentum L equal to 1. The quantum variant of equivalence principle would be extremely strong. This generalized acceleration would be concentrated at these two-dimensional singularities. There would be analogy with Brownian motion. Fermion pair creation and boson creation, they would correspond to partonic orbit turning backwards in time at the two-dimensional singular surface. The regions outside the singularities, they would correspond to massless fields, their geometric counterpart. At the singularities, Higgs field is non-vanishing, so that it will be mass present. The analog of Higgs vacuum expectation would be non-vanishing only at the singularities. Exotic differential structures in 4 dimensions, particle vertices, and the new view of gravitons. One can start from a problem: how to avoid separate conservation of fermion and antifermion numbers, making the theory trivial. The idea that all bosons are bound states of fundamental fermions is extremely attractive and is the only possibility in TCD framework. It however leads to a problem. The numbers of fermions and antifermions appearing as free particles and building bricks of bosons are separately conserved. This can't be true. The conservation for the total fermion number, can be stated as the vanishing of the divergence of the fermion current, defined in standard manner. Here, gamma alpha are induced gamma matrices or modified gamma matrices defined in terms of bosonic action. Induced gamma matrices seems to be the correct identification, as I have already argued. The vertex should serve as a source for the modified Dirac action, since this equation can't be satisfied at a vertex. And at this vertex, these gamma matrices, the covariant divergence should be non-vanishing. The trace of the second fundamental form must have this delta function singularity. This is true. And in this picture, the pair creation would correspond to fermion line which turns backwards in time direction. This direction could be also some other direction, and in standard perturbation theory it could be so, even space-like. And it should be normal to the singularity at this two-dimensional partonic surface. This is an intuitive picture, and the turning back in time direction. This should have some deep meaning. And this could explain why we can have this apparent non-conservation of fermionic current. The time direction in which conservation holds is changed, and this explains why this divergence is non-vanishing. So there is also the question whether one should identify the spinor fields which emerge from vertex as C and its CP conjugate. And this could mean that the two particle orbits, the incoming and outgoing in opposite time direction, correspond to generalized complex conjugates of each other. The anti-analyticity and analyticity, they would correspond related by CP conjugation. There would be geometric realization for CP conjugation. This is an intuitive picture. What X-Helix move structures could have with fermion pair creation? Four-dimensional spacetimes are unique, in the sense that they allow an infinite number of exotic move structures. Apart from a subset of measure zero, they are reduced to ordinary standard smooth structures. These subsets of measure zero are physically analogous to defects. The simplest defects are point defects, but one can also imagine higher dimensional ones. And the two-dimensional defect seems to be the maximum dimension. So this means a serious difficulty for general relativity. Should one try to get rid of them by some principle cosmic censorship, or should one try to find an interpretation, physical interpretation? So the natural question is whether minimal surface property for spacetime surfaces as generalized complex surface fails at least defects. These singularities are analogues of poles of analytic function, so that one can ask whether the identification of defects of the ordinary smooth structure with singularities at which the minimal surface property fails with and identification as generalized poles and other singularities where the generalized holomorphy fails. Could this kind of identification make sense? The three-dimensional light-like orbits or partonic orbits, string vertices, strings, and points at which light-like orbits of fermions turn around, could they correspond to these singularities identifiable as generalized vertices? So, could red effects be essential for the definition of creation and annihilation vertices for fermion-antifermion pairs? The intuitive picture would be that fermion turns backwards in time in this kind of vertex. How this picture could allow the construction of graviton vertices. In quantum field theories, a standard approximation is to replace the gauge boson at the vertex with a classical gauge potential. In TGD, there are no fundamental quantized boson fields, and this replacement is the only possibility. This would correspond intuitively to a turning of fermion line at the orbit of a partonic tool surface backwards in time. Could these kind of surfaces be identified as defects of the ordinarily differentiable structure, which would be actually exotic smooth structure in more advanced treatment? Could this allow to get rid of the problem that Dirac equation and conservation of fermion number are apparently broken in the vertex, so that only sum of fermion and antifermion number is conserved? So, modified Dirac action should give rise to fundamental vertices. The modified Dirac equation is satisfied almost everywhere, but forces it to zero, so that action would be trivial in the gauge theory sense and no vertices would be obtained. At the singularity, the modified Dirac equation would fail. Also, the fermion current is apparently not conserved. One would obtain a delta-like singularity function like singularity given the analog of standard classical vertex for the creation of fermion pair or a particle with spin smaller than 2 as a bound state of fermion and antifermion. Interesting quantum physics would be possible only in space-time dimension 4. Gauge theory graviton duality suggests that gravitons indeed correspond to fermion pairs and to the Minkowski part of the second fundamental form, defining a spin-1 object at the boundary. Now boundary would correspond to partonic orbits and a spin-2 object in the interior, rotating flux tube and the wormhole contacts. There is still a comment about Lorentz group theories, gauge theories of gravitation. The basic problem is that unitarity does not allow this kind of theory. Unitary representations are infinite dimensional for Lorentz group. In TGD, this kind of representations are, however, very naturally associated with the causal diamonds, intersections of future and past directed light cones, and they are indeed basic objects in the zero-energy ontology of TGD. One can also solve the Dirac equations for spinors inside CD, and one obtains a solution space as unitary representations of Lorentz group instead of Poincare group. The Poincare invariance, which is problematic at the level inside CD, translational symmetry is lost, would be realized in the moduli space of causal diamonds. And one would have inside CD kind of Lorentz group based gauge theory, but would have infinite dimensional representation, unitary representation, as in also in the case of translational invariance. Then one would have infinite dimensional representations of translation group. The unitary representations of Lorentz group would indeed appear naturally in the Dirac equation for causal diamond. Future light cone can be regarded as a slicing by the hyperboloids H3 parameterized by the light cone prototype. One can classify the solutions to the representations of Lorentz group at the hyperboloid, and SO1 quantum numbers would appear naturally in the graviton vertex. Also mass would of course appear. So one could understand the basic vertices as a splitting of two-seated closed monopole flux tubes with Euclidean wormhole contacts at the ends. The flux tube would produce two flux tubes. The splitting of the flux tube would be a generalization of reconnection for closed strings. The simplest reconnection would involve a creation of fermion-antifermion pair, such that fermion and the antifermion would go to wormhole contacts over separate flux tubes. For defects of the smooth structure, the topology of free surface would be between two topologies. This would add a further interpretation for these defects. The pinching of torus producing two spheres represents a basic example of this. What about the earlier proposal that gravitons are pairs of fermion pairs, two fermions, two antifermions? This would give entire graviton spin. Graviton emission vertex would involve two separate vertices, this kind of spin-one vertices, in an essential way. This is possible, but I'm not sure. Does it look really elegant? And it would also conform with the idea that gravitation is in some sense a square of gauge theory. But to me, this does not look an attractive idea. And it is also difficult to see how the basic properties of gravitational coupling, in particular the appearance of gravitational constant proportional to CP2 length squared, how it could emerge. These are difficult to understand for this option. What about gauge boson vertices? To understand how one could obtain gauge boson vertices, one must study in detail what happens at the singularities. The modified Dirac action contains two terms. First term involves covariant derivative of psi, and second term the covariant derivative of its conjugate. Here modified gamma matrices are induced gamma matrices or proportional to them. In order to obtain non-trivial gauge boson vertices, the contraction of induced gammas with vector potential should have a delta function singularity at the vertex, which corresponds to two singular two surface and the light-like orbit of partonic, light-like surface defining the partonic orbit. It forms an interface between Euclidean and Minkowskian spacetime regions. Apart from this singular two-surface, the second fundamental form vanishes identically, also at the partonic orbit. The reason is that it does not have common non-vanishing tensor components with the induced metric. This is a purely algebraic fact. At the singularity, the breaking of generalized analysis must occur. Embedding space coordinates are not anymore functions of generalized complex coordinates of the space-time surface, say u and w, but functions of also v and w at the singularity. Singularity would be like a pole of an analytic complex function. It forms an interface between Euclidean and Minkowskian spacetime regions. Apart from this The covariant form metric, not only the free metric, is degenerate and effectively two-dimensional at the partonic orbit. In light-like coordinates uv for a Minkowskian spacetime region, the induced metric has a form in which is non-diagonal. U and V, no diagonal components, W and conjugate, no diagonal components. It becomes degenerate with respect to U and V since generalized complex coordinates for the embedding space depend only on U or V, but not both. So that also the non-diagonal components GUV and GVU vanish. The tangent space of the spacetime surface at partonic orbit is metrically two-dimensional, since the determinant of the form metric vanishes. The contravariant metric multiplied by this determinant behaves like two-dimensional delta function, singularity at the partonic surface. The modified Dirac equation must be true outside the two-dimensional singularity x2. The delta function like singularity requires vanishing of the covariant derivatives of psi, both with respect to U and V. Generalized holomorphy of psi would guarantee this outside the two-dimensional singularity. At this singularity, psi depends on both U and V, rather than only either one of them. At the singularity, two-dimensional singularity, second fundamental form is its trace is non-vanishing, and components of the induced metric in these light-like directions are non-vanishing. Diagonal components are non-vanishing. This reflects the failure of hypercomplex analyticity. Assuming that the determinant of metric vanishes also now, one obtains a delta function like singularity for a trace. The induced gamma matrices are combinations of both gamma U and gamma V. This reflects the failure of this analyticity. Both AU and AV, the components of induced vector potentials, appear at the vertex and are multiplied by the delta function. By the loss of hypercomplex analysis, the Dirac equation at the vertex fails to be satisfied. This implies the non-vanishing of this gamma mu A mu, giving rise to the vertex. So, what does this two-dimensional singularity look like? Fermions should turn backwards in time. This is an intuitive picture. At the vertex, the time coordinate, call it big T for Minkowski space, for the partonic orbit must have extremum, turning point. Therefore, the derivatives of this big T with respect to the coordinates of the two surfaces must vanish. Time stops. As a consequence, the derivatives of the coordinates of two surfaces with respect to T diverge. And the two branches meeting at the singularity could correspond to hypercomplex hypercomplex analytic anti-analytic functions. That is, functions of U V. And this would explain why hypercomplex analysis fails at the vertex. A more general condition would be that the meeting fermion lines correspond to complex analytic anti-analytic functions, also W and also CP2 complex coordinates. Fermions and antifermions would correspond to complex conjugates of each other as four-dimensional surfaces or space-time regions. Single connected space-time region would be either analytic or anti-analytic, and therefore contain only fermions or antifermions. This might relate to the matter-antimatter asymmetry. If so, then the proposal that quantum coherence is realized in arbitrarily long length scales would receive strong support.